all the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Hello everyone, I'm Megat Michael. I'll talk to you today about hazard pointer synchronous reclamation beyond concurrency TS2. So first I'll start by just giving very quick background about hazard pointers. It's a mechanism for safe reclamation. Basically, one thread owns a hazard pointer and it communicates through it to other threads that may remove the object that they want to protect concurrently while the thread wants to access it. So the protocol between the threads is quite simple. You can see here, like there's a thread who wants to protect an object and another thread that wants to remove it and reclaim it. So the thread will read a pointer from an atomic source, and that's the one say, okay, let me try to protect it. It's going to set hazard pointer to it. So now it's saying, okay, maybe it's protected, but only if it hasn't been removed yet. It checks that it hasn't been removed. So now we know that the thread knows that it's protected and it can access it safely. It goes ahead and, the other thread removes it, but it doesn't matter. It removed it, but it hasn't reclaimed it. Now the user or protector thread accesses the object safely, and then when it is done with it, it clears the hazard pointer, and it is like it's okay for on the other thread to reclaim that object. So now that object checks the hazard pointers, it's not protecting the object, and it goes to safely delete the object. So that's kind of like in a nutshell how it works. As many of you know that the working draft for concurrency TS2, the technical specification, has been submitted, and there's going through the TS process. So there's a larger interface for hazard pointers, but this is like the essential interface. There are like a hazard pointer class, and it has many members, but mainly protect is kind of like the main function. And there's a base class for objects that are protectable by hazard pointers. And there's really one function there, it's retire. It's telling, it's basically handing off the object to the hazard pointer library to say, okay, reclaim it whenever it's safe to do so. So looking at this example here, using that kind of interface, this is like a typical deferred reclamation example. You have a shared data, but it's frequently accessed and used and infrequently updated. So we want the read and use operation to be actually as fast as possible, and the update should be efficient, but we don't care as much. So for the read and use, it's going to use a hazard pointer, and that uses a function in the interface called make hazard pointer. That's a non-empty hazard pointer that you can use, and it uses that to get a pointer to an object that is protected by a hazard pointer from an atomic source. Once it gets that, now we know that as long as the hazard pointer is alive, that object is protected. And it can go ahead and pass it to a function. That function can use that pointer as, however it needs, and we know it's protected. On the other hand, you have the update operation. If it removes that object, it cannot just delete it right away. It has to pass it to the library using the retire function. And just to remind people why we use hazard pointer, it's fast, it's very fast, it's faster than even a single atomic instruction, and it supports protection there's no limitation on the duration of protection. Okay, so moving on to what happens to retired objects. I mean, it's like we cannot just accumulate retired objects. It's really the library, otherwise we'll run out of memory, so the library does asynchronous reclamation. Basically, it doesn't guarantee the timing of the reclamation. It just says that we're gonna do frequently, pardon me. Oh, how do I get rid of that?
Where is your click with your?
Oh, maybe this in, but that's intro.
Okay. And go right ahead.
Oh, thank you. Sorry about that. So asynchronous reclamation, it happens in the implementation in the Folly library, which is open source, is that it gets invoked whenever we accumulate some number of objects that are retired and not yet determined that they are reclaimable or not. So the way to do to have that kind of asynchronous reclamation to be amortized, to take constant time per object, is to accumulate as many or twice as many objects as the number of hazard pointers in the process. So we know that we cannot protect more than the number of hazard pointers. So if we accumulate twice of that, then we know that we'll at least reclaim as many hazard pointers. So the steps to do asynchronous reclamation is to first extract the objects that we plan to check for whether they're reclaimable or not. Then we read all the hazard pointers and collect these values, and then we match the addresses of the objects against the hazard pointer values. Whatever match addresses that match, then we know that these are protected and we cannot reclaim them. So we push them back into the domain, or the global domain in this case. And when we do that, then finally we can reclaim unmatched objects. So that's how in general it works. So this, as I said, this allows to bound the number of reclaimable objects that are not yet reclaimed. But there's no guarantee for the timing. So let's look at the answer. Look at the question: is asynchronous reclamation always enough for the use cases? And so we can look at this example here, like sequence of events. And here we're not using hazard pointers. We're not using deferred reclamation. We're just doing the delete the object right away when we remove it. So there's no problem. So here we have a type that the destructor depends on some resource X. And when we do the deletion, we're gonna use that resource, but then later on, that resource is shut down. So far, no problem. But then what happens if we use hazard pointers or deferred reclamation? Here we have we retire the object, but we haven't reclaimed it. So, and now we shut down the resource X, and then there's no limitation on asynchronous reclamation. It later does the reclamation and finds that that object is reclaimable, and it deletes it. But now we're using an unavailable resource, and we crash. So some use cases need more than that, need synchronous reclamation. So now let's get back to the concurrency TS2. Everything clear so far? Yeah. So getting back. Oh, please go ahead. But please speak up because my hearing is not good.
Yeah, synchronous reclamation. Does this mean there's a background thread running and calling it?
The question is whether this matters, whether there's a background thread or not. Yeah, it doesn't matter. It could be the same thread that's doing retire is like doing the reclamation, or asynchronous reclamation, because it might decide, the decision to do asynchronous reclamation is actually quite long. Like, let's say a system has 20,000 hazard pointers, then we might wait for 40,000 objects. But yeah, background thread, the same thing. Yep. Okay. All right, so going back to Concurrency TS2, it provides an interface for doing synchronous reclamation. In this case, it's called hazard pointer cleanup. And what it does, it actually guarantees that any object that was retired before the call is invoked and was not protected by any hazard pointers before the call was invoked, then we guarantee that it will be reclaimed before we return from that call. So it's quite strong guarantee. So let's look at it, how it can be used for our example. Going back to our example, so now we retired the object, but then we know that we need synchronous reclamation, so we're gonna call hazard pointer cleanup. And because it's not protected, it's gonna delete the object and no harm done. So it works, but let's look more into this. So yeah, as I said, it's a simple, strong semantics, but does it perform well? Let's look at what it entails to do this global cleanup. It's guaranteeing this cleanup of all the objects that were retired. So it must collect all retired objects, and even including private caches. So that's kind of overhead already. It checks all hazard pointers. That's as usual, like it has to. And it has to complete the reclamation of all unprotected objects before returning. And actually, even more complication, it has to wait for any concurrent asynchronous reclamation, because now some other thread is doing asynchronous reclamation. We don't know how long, how fast it will do that. So we want to guarantee that we're waiting for it before we return, because that's the promise we give for global cleanup. So it is scalable. It's definitely not scalable. It's slow and not scalable. Now it's also, there's another extra overhead that even if we don't use global cleanup at all, we're actually causing a slowdown in for the regular use case. So let's say we have thread local caches of retired objects. Without global cleanup, we can just use sequential data structures. It's like just one thread. It's a thread local. It's one thread accessing it. We don't need synchronization for that. But then now, because we do have global cleanup that has to extract these objects from the thread local structure, now we have to use extra synchronization. And actually, recently I just removed that capability from the Folly library, and because we support sharded lists in the domain, so it's the same synchronization without the extra headache. So that's kind of a downside of supporting that. Now let's even inspect this kind of interface even further and say, is one call to global cleanup always enough? And in this example, actually the answer is no. So what if we have counted links? It's kind of like we don't retire automatically. We just do we actually retire the object only when it doesn't have any more inbound links. So in this example, we have object A is holding the only remaining link to object B. So some thread removed A, which implicitly removed B because that's the only link to it. And A has no more inbound link, so A is automatically retired. So the thread says, okay, I removed all the objects of that type, but I really need synchronous reclamation, so let me call hazard pointer cleanup. And it's thinking of we need to reclaim A and B. But then in this case, cleanup will reclaim A because it has been retired before the call. But B is only retired during the call. So it's not even covered by that guarantee. So now we have resource X gets shut down, but then B hasn't been reclaimed yet. So actually, we need more than the interface in TS2 in this case. How do we remedy this? Solutions might be, we can have like user code, like maybe we have an indicator in when we retire the object, like let's say when we retire A, when we retire B, we have an indicator. Now the thread, when it is about to do global cleanup, it clears that indicator, but then during cleanup, the indicator gets set again, then now the thread knows, oh, okay, let me call cleanup again. And again. So if we have like kind of, let's say a succession of like 3 of such objects that are pointing to each other, linked to each other, then we would call the cleanup like 3 times. So that's in user code, but where in user code? It's actually, these things can be like, you know, including code by thousands of engineers in many levels of the software. So we really don't know where to keep that kind of logic. So in the Folly library, we actually put that in the library itself, in the hazard pointer library, but that entailed integrating link counting in the hazard pointer library. So we have this capability in Folly. But then, I mean, that's, there are still downsides. So now actually when we do asynchronous reclamation, because it's interacting with synchronous reclamation of global cleanup, now we have to, whenever asynchronous reclamation retires a linked object, it will know that, and it will know that to do another round of asynchronous reclamation. So I said that asynchronous reclamation is quite expensive because we might have like, you know, as tens of thousands of hazard pointers. So, but we amortize that. So that's why it's okay to do that in asynchronous reclamation. But now we retired maybe just a handful of more objects, but now we have to go again and read the hazard pointers again, and maybe multiple times as we go through a succession of links. So that's a downside that is caused because we want to support global cleanup. So let's look at another option, okay, to say, well, maybe because the global domain is so big, it has like tens of thousands of hazard pointers, why don't we use custom domains? Yeah, that might work. So here's a code example of using that. We're just like saying every container will have its own domain. And when we retire the object, we'll just retire it to that domain. That can work. I mean, it will work. It's just if the domain is very contained and the number of threads that use that container is like small, and the objects are, the instances of the container are long-lived. So it's like to make it worthwhile to construct new hazard pointers for that domain, and then when the container is destroyed, we destroy the domain, and it guarantees this synchronous reclamation. But then we have all this overhead. But what if we have, large number of instances of this container? Like, for example, Folly concurrent hash map. There's all kinds of uses of that. And then some of these containers can be used by thousands of threads. And now we have the overhead of constructing all these new hazard pointers and then destroying them all at the end of the domain, the lifetime of the domain. So it's not a good general solution. It's not robust. So the question, are there any good solutions for the default domain, or even any good solutions? So the answer is something called cohorts, and I'll explain that in a minute. So a cohort is a set of retired objects. So a retired object can belong to at most one cohort. And the guarantee of the cohort is different from global cleanup. The guarantee is that the completion of the destructor of the cohort guarantees that all the objects that ever belong to that cohort must have, the destructors for these objects must have completed already. So that's kind of like so you can imagine that, like, let's say in a hash map, and the keys and values are user defined. So we don't know the dependencies of these types, right? So we're saying, okay, when we let's say we put a cohort in each hash map, And now we say at the destruction of the map, where we guarantee that we're going to destroy the cohort, which guarantees that we're going to destroy all the items with keys and values that ever belong to that map, because we associated with that specific cohort. So anyway, that's kind of like the general idea. So it has weaker and stronger semantics than the TS2 cleanup. It's weaker because it doesn't cover all retired objects. So it's definitely more specific, but it's stronger because it actually does this kind of dependent retirement and link structures seamlessly without having to repeat reclamation and checking hazard pointers over and over as we traverse these links. Okay, so let's look at the proposed interface for that. I mean, I have a different interface in the Folly library than that, but this is would be kind of a cleaner one where we just have a cohort, and it's all what we need from it is just a constructor or destructor. And of course, we have to have the semantics I mentioned about the destructor. It provides that guarantee that it will guarantee the reclamation of any object that ever belonged to that cohort. The base class for the objects is just it needs to be aware of cohort. It could be the same base class as in TS2 or a different base class. It just needs to support something to set the cohort, like saying, okay, when this object is retired, it's gonna be belonging to that specific cohort. So let's look at how. If I'm going too fast, let me know. Any questions? Okay. So we're looking now at the same example I showed for the custom domain. So actually, cohort is a good replacement of custom domain. Please go ahead, but speak up.
Does this container no longer move or copy?
You can make it do that. I mean, I want to simplify this. You could have the cohort being a pointer to cohort. So, let me repeat the question. The question is does that make the container not copyable or movable? And yeah, I mean, in this example, it wouldn't be, but there are ways around that. I mean, basically, you just have a pointer to the cohort. So it wouldn't be movable, but it would be copyable, because then you can just copy the object, but then now they'll have a different cohort and have a pointer to that different cohort. Okay. So in this case, we actually make a cohort part of that of each instance of the container, and we associate any object that gets retired from or removed and retired from that container to that specific cohort. And automatically, when we destroy the container, we're going to destroy the associated cohort, and that will take care of the synchronous reclamation that we need. So this is not global cleanup, but it's actually is doing what we want from this case. Okay, so looking, usually in the standards committee, we don't talk about implementations, but implementability is very important. It's like if it doesn't work, then what's the point of proposing an interface like that? So implementation requirement, we want it to be fast and scalable, because I mean that's what the problem we're having with global cleanup. We want to support transitively dependent retirement. I claim that it does that, and it needs to support the hierarchies of, let's say, maps of maps of maps. They might be like a cohort that leads to the destruction of objects that actually include cohorts and so on. So we have to support that, like that kind of hierarchies. And of course, it has to interoperate with asynchronous reclamation, because we cannot just accumulate these objects in the cohort and not do asynchronous reclamation, because otherwise we'll run out of memory if the container is long-lived and keep churning out removed objects. So we need to work with asynchronous reclamation. So looking at a basic cohort implementation, we would have, like, there are some, so far these are optimizations. We don't need to have it, but it would be good for optimizations. Like, we need to remember whether did we push any objects to the domain or not. If we haven't, then we don't even need to check anything with the domain. We can maintain like a a cache of objects before we push them in bulk to the domain instead of like going to the domain very frequently. So yeah, that we would have like a threshold to say, oh, we accumulated that many objects. Okay, now let's push them to the domain. But then in the domain, we need to have a list or a set of objects that belong to cohorts, and that list needs to be lockable. I mean, we need to be able to lock it, because why do we need that? Because we might have multiple cohort destructions happening concurrently, and we don't know which objects belong to which cohort. So we need to sort them out. So we need to synchronize between these cohort destructions. So the pop operations are like they have to synchronize, but then the push operations are lock-free. They can just like keep pushing into that set. What does the destructor of a cohort do? It goes and pops the objects that potentially could belong to it, right? So it's like it doesn't know which belongs to it and not, and it locks the list because it may extract or pop objects that belong to other cohorts. Now it just extracts the object that matches its own identity, and then it pushes back the unmatching objects and unlocks the list, just to allow another cohort to, like, destructor to do its, the same operation. And then, without holding the lock outside the critical section, it reclaims the matching objects. It does not need to check hazard pointers, because we're destroying the cohort when we're at the end of the use of these objects that belong to the cohort. It's like we're guaranteeing this is synchronous reclamation, where we really need to destroy these objects. There's no follow-up to that. And as I said, while a lock, because concurrent cohort destructors. All right. Now let's revisit asynchronous reclamation, because now we need to make it work with this kind of mechanism for synchronous reclamation. So now the asynchronous reclamation, now it needs to work on cohort objects. So now it pops all these objects. It locks the list, because again, there might be concurrent cohort destructors. It reads the hazard pointers, because it needs to check and match the addresses against hazard pointer values. It does the matching, and this is like a little bit high overhead. It actually needs to reclaim unmatched objects under the lock, because once it releases the lock, it's there's no guarantee how fast asynchronous reclamation will do call the deleters. So it's otherwise we would not be respecting the guarantee that we're providing about the destructor of the cohort destructors. So it does the reclamation under lock, and then it pushes the matching objects back into the domain cohort object list and unlocks the list. That lock needs to be reentrant in this and under this algorithm, it needs to be reentrant. Because why? Because we could be doing asynchronous reclamation of an object. That object itself, its destructor, entails the destruction of a cohort, and now we have to execute the cohort destructor synchronously, and we're already holding the lock, so we need to make that lock reentrant in this case. Everything clear so far? Okay. So can can the domain, I mean, now we're saying we're locking the list. It's kind of like it has a lock on it. Concurrent cohort destructors like have to lock that list. So it sounds like this is like a bottleneck. And actually, asynchronous reclamation is also holding that lock for while it is reclaiming objects. So I mean, that sounds like a bottleneck. So why don't we shard that list? The problem is we can have this kind of scenario where, I mean, without going to too much detail, but you can see like, okay, we're doing asynchronous reclamation of an object A. It has like includes the destruction of a cohort C0, which belongs to a shard 0. And then, but that contains another object B0 that entails the destruction of a cohort C1, which belongs to a different shard. And now we could get into a situation where we have like circular dependency and deadlock. So under this algorithm, we can shard the domain cohort object list. So you might be asking, I mean, I said fast and scalable and robust. So far, it isn't really. So let's revisit that. Okay. So the cohort, let's revisit the, go ahead, please. Can you speak up?
Is there a scheme to decide which retired objects go into which cohort?
Is there like some key or something? Right. I mean, the object. So the question is there some way to identify the cohort from the object, right? Or
is there a way to? So I have a retired object.
Right.
Is there a way to figure out which cohort it goes to? Is there a bunch of cohorts?
So I'm not sure I'm answering the question, but I'm gonna say like the before retiring the object, we're actually associating with a specific cohort. So far, clear so far? So now like the object, whenever we look at the object, retired object, we know which cohort it belongs to.
How do you identify it? Why do we even do that thing in the first place?
Right? How do I? It's actually we include the cohort identity in the object-based structure. Does that answer your question? Okay. So
the question is what determines which cohort?
I can't hear you. I'm sorry. Can someone speak up?
So the question is like, how do you determine which cohort a retired object should go to?
Which cohort it should go to, right? Oh, very good. Let me just back up a tiny bit. Let's go to this example, for example. Okay, so now we have a cohort that belongs to the container. That is the cohort that all the objects belonging to that container will be associated with. Does that clarify? Okay, so let's look at this. When that container is destroyed, the cohort will be destroyed, and all the objects that were retired, were removed and retired and associated with that specific cohort will also be guaranteed to be reclaimed. Clear? Okay. All right. So, go ahead.
So what happens if this object has other objects that don't belong to any cohort?
If I have other objects that don't belong to the cohort in that container? No, it's my job as the programmer of that container. I'm the developer of that container to, it's for correctness, I have to associate it with the cohort.
But then the object itself has a pointer.
The object itself?
The object within the container, right? So let's say you've got this etc. And there's another pointer that doesn't belong to this container.
No. These objects are they belong to that container. It's like the type, let's say.
Another pointer. There's another pointer within the object.
No. It's like each object can be one cohort only. Is that?
Yeah, but then there's a nested pointer within the object.
Sure. Like you're saying, let's say that object contains another container. Sure. Yes. So when we destroy that object, we'll have to destroy the container that it's controlling, and that might be a big, yeah, we have like maps of maps of maps. That can happen.
It's not a map. What if it's just a single pointer that doesn't belong to any
Po-
cohort?
when you say pointer, then the pointer will entail the destruction. You know, will destroy what it owns, right? Yeah. So that and it can be a different type of a container or not. So yeah, it can handle.
What happens if it doesn't belong to any cohort? Would it be kept in the retirement list?
Sorry, I can't follow what you're saying, but if someone can.
So what if it doesn't belong to any container?
Oh, if it doesn't belong, then that means we don't care about its synchronous reclamation for it, or we're gonna use like global. But I mean, I'm claiming that actually we don't like we can use cohorts to manage that synchronous reclamation. So it's the responsibility of the higher level programmer just above the level of hazard pointers to know which cohorts to use. So and this example is kind of like it's a small one but complete in saying every object that is like we're gonna remove and retire from this container, we're gonna associate it with that cohort, and then automatically it will take care of synchronous reclamation. Okay. All right, getting back to how do we make this mechanism, change the algorithm to make it fast and scalable? All right, so what are we going to add to these structures is that the cohort will have an object of a list of reclaimable objects. So these are objects that have already been vetted by asynchronous reclamation and identified as reclaimable. So it's kind of like we're saying these are ready to be reclaimed. You don't need to check hazard pointers. And we'll provide like mechanism for the domain. So this is kind of internal. It's not exposed to higher level users. Just like push reclaimable objects, for example. On the other hand, then we will be able to shard the list in the domain. So that's, and I'll show how we do that in the next slide. So we have a list in the cohort itself, and now we can shard the list in the domain. So now let's revisit asynchronous reclamation for the third time. Now, what it does, it will pop all objects from the domain, including the cohort object list. But in this case, it will be like multiple shards, and it will lock all the shards. And then it will read the hazard pointers, and it'll match addresses against the objects. But then instead of in the previous algorithm that I mentioned, it was actually reclaiming the object under lock. Here, we don't reclaim unmatched objects under lock. Instead, we push each object in its corresponding cohort's list of reclaimable objects. So it's like kind of where the asynchronous reclamation becomes not responsible for actually deleting the object, but just like passing it on to the corresponding cohort. So this way we disentangled asynchronous reclamation from the reclamation of cohort objects. And now we push the matching objects back into the list or the lists and shards and unlock the shards. So it's a shorter duration of holding these locks. So what happens in the cohort is that occasionally, whenever a thread needs to, let's say, retire an object to a cohort, it will just check that list. Is this list empty? If not empty, it goes ahead and delete the objects that have been determined already by asynchronous reclamation to be reclaimable. A good side effect of that is that cohort objects are reclaimed only by related threads that retire objects to that specific cohort. So that's kind of like it's a good side effect because there's like a always kind of downside of having threads have nothing to do with an object and do the reclamation for it. Another good side effect of this algorithm is there is no reclamation while holding any shard lock. And now the locks on the domain shards don't even need to be reentrant. So it's like really simple locks.
I have a question.
Go ahead.
So, is there a reason you're popping the objects from the list instead of just iterating through it?
Sorry, speak up.
Is there a reason why you're popping the objects and then matching for addresses instead of just
Yes.
going over the list?
Yes. So it's kind of I'll repeat the question that what if I heard it correctly? Why are we popping the objects from the shards before checking the hazard pointers? Right. No, but in this case, it's kind of pop and lock is actually one operation. It's kind of we actually have a bit in the head pointer to the list. So we're kind of just like saying pop and lock is actually one compare exchange. And then why are we popping all of them before reading the hazard pointers? It's kind of that's kind of needed synchronization to guarantee the correct ordering. Okay, all right. So that's kind of the improved algorithm for cohorts. Another question or? All right. Oh, time. Right. So now that I talked about this implementation, let me just go through the experiences that we gained from the Folly implementation of hazard pointers. It's heavily used through indirectly by thousands of engineers that are using data structure in many different ways that are dependent on synchronous reclamation of hazard pointers. So Folly is available like an open source on GitHub. It arose that we need synchronous reclamation. Then we used global cleanup as in TS2. That was that we needed stronger cleanup for linked objects. And then it's just too expensive. We couldn't include a global cleanup in every destructor of a concurrent hash map. It's just too expensive. So then we had users who, higher level users who need synchronous reclamation who say, okay, why don't you use global cleanup when you need it? But then sometimes it's too late to do that. After you destroy the map, who knows what's happening in the system in between? The resources that the types may depend on might have been already shut down. So that prompted the development of sharded cohorts in the first try. Everybody is happy, but then one user said, I'm getting deadlock because they are using maps of maps of maps. So now we have to backtrack and say, okay, let's make the list unsharded. And people were happy with it for a long time. And actually, we migrated from global cleanup. It's almost like it is deprecated effectively. It's only using it for micro benchmarking and testing. But then, last year, one user said, "This is the unsharded list blew up. It's actually it just couldn't keep up with it. It just kept growing and growing and growing, and it's actually being locked. It became a bottleneck that just because that user was doing frequent retirement, removal and retirement. So that prompted this kind of improvement in the algorithm, and now so far everybody's happy. So let's move on to a related question is there are some users, they think they need synchronous reclamation, but all what they need is actually quasi-synchronous or quick async, on-demand invocation of asynchronous reclamation. So let's say someone is like removing an item from a container, but that item is like hundreds of megabytes. And they really don't want to wait 2 seconds for that to be reclaimed, or for the next like asynchronous reclamation, or whenever we accumulate tens of thousands of objects. So they say, okay, it's like they don't care about performance that much because they are dealing with massive data. Then they invoke global cleanup. In this case, actually, we don't really need the semantics of global cleanup or synchronous reclamation. We just potentially could provide to them like on-demand asynchronous reclamation. Just go ahead and do asynchronous reclamation, even if it is not efficient in an amortized way. And there are like a few options there that like we're considering if the need arises. Okay, so now I'm gonna shift gears to a roadmap for synchronous reclamation. So the Concurrency TS2, the working draft is available. It has global cleanup with the semantics of hazard pointer cleanup. Feedback is welcome. I mean, the TS is not out yet, but of course, anybody who like implements it or looks at the interface and gives feedback, then that's very welcome. The plan for proposal for hazard pointer in C++26 is to be a minimal useful subset of what's in TS2. Why minimal? Because we only want the stuff that we really have high confidence in its usefulness and that it's like it will survive the test of time. And also, we don't want to impose on the committee's time is very limited, so by having a proper subset of the TS, things that have been already vetted through this whole process would require less of the committee time. How about cohorts? It's actually, I have very high confidence based on the Folly experience that it's quite useful and in some use cases needed. So it's kind of like we want to expand the usefulness of hazard pointers. Why not C++26 maybe, but it's unlikely because it will require complex wording and that will take more of the committee time and might not fit within that time frame. But eventually, I'm quite confident that some form of cohort support would be added to hazard pointer interface. How about global cleanup? We're waiting for or depends on the feedback that we get from the TS. Do we need it? Do we need to make it even stronger, make it transitive cleanup if we add integrated link counting, as in Folly? Or actually, maybe we'll go back in Folly and remove the global cleanup. So it's kind of, that's kind of in flux whether we need that or not, and whether we need to add other extension like support for quasi-synchronous on-demand asynchronous reclamation. Okay. So now let's very quickly, this is like beyond this is kind of like a minimal proposal that we have in mind for C++26. It supports only asynchronous reclamation. I mean, that's useful in its own way. It's useful. It just doesn't have synchronous reclamation. So beyond that, that would be like a preliminary interface. I kind of covered it already. Just need like support for cohorts. It's just like constructor, destructor, some kind of object base, whether it's a separate kind of a different cohort object base, different from the object base, or depending on subject to ABI compatibility, we would just add this capability to set cohort to the object base that we already want to propose for C++26. And finally, these are the references looking at Folly on GitHub. The working draft is already available. And if you haven't already attended our talk yesterday with Michael Wong and Paul McKinney, then give it a watch because we discussed like the TS2 in more generally. And thank you for your attention, and I'd be happy to answer any questions you have. Thank you. Please. Yeah, please.
Given that we are interested in standardizing a minimum set of features for C++26, would not the extension to support the global synchronous allocation strategies outlined in the talk present like implementation difficulties to scale? Like if there's a minimum set of features standardized first, and then we introduce synchronous strategies with like cohorts and etc., would that not be difficult for implementers? Is there a concern there?
Okay, assuming that I heard you correctly, you're asking like the minimal subset for C++26 does not include synchronous reclamation. So your question is like, should we provide some support or so yeah, the question, like the issue why we're not providing support in the proposal for 26 is that, well, the global cleanup, that's the one that has been vetted through the TS process. But then, as you have seen, it's kind of like we're not sure that actually will end up supporting that. And also, it does have might have negative effect on implementation. So we don't just like say, well, it's better than nothing, and we support it, right? I mean, and cohort is actually, yeah, even though it's with confidence, we might need time to get the right wording especially when we're specifying the semantics of the destructor of cohort. So that kind of like that's the thinking behind what we want to propose for 26. I hope I answered your question, but I apologize if not.
If I reword it,
Oh.
Could the introduction of cohorts be an API break after standardization of the minimum set of features from TS2?
Oh, could the addition of cohort be an API break? Yes, that's why it's all like the object base that might be an API break, because we're right now it doesn't have cohort, but then now we're going to add cohort. So yeah, that's definitely, that's why when going to the committee with plans for 26, we're kind of like show the roadmap for all these different things that we talked about in the other talk. Like, synchronous reclamation, integration with link counting, because like now we need a counter in the base object. That's ABI break. So yeah, definitely we need the committee to be aware of that. If we can codify that in 26, and we're kind of like opening at least some runway for us, like to add things, that would be great. If not, I mean, we still have option to have different types of object base. I mean, we have that in Folly and say, oh, this is the link type that has link counter. It's a separate one from the regular object base. I didn't bother to have a different type for cohort, but so actually added cohort to everything, but we didn't have to. So we could get around the ABI issue by adding more types if needed. All right. I suppose, yeah, we don't have questions from online because we're not broadcasting yet. All right. Okay. All right. If no more questions, thank you again for your attention, and thank you.